Hi, I'm Keunwoo Park. While I interned at the Hasselplanter Institute, I worked on laser cutting. You can see a user assembling a chair model. Here, the user wants to insert the leg piece, but picks up an incorrect piece and recognizes that it does not fit. FoolProofJoint solves this issue by making pieces identical, thus interchangeable. Second, it is possible that the user might try to assemble a piece in the wrong orientation, causing the piece to not fit. FoolProofJoint addresses this issue by making pieces symmetric. Third, the user wants to assemble the backrest here, and there are two similar looking pieces. However, one of them does not belong to the backrest, but it still fits there. Subsequent pieces might continue to fit as well, producing a propagation error, resulting in a frustrating disassembly process. FoolProofJoint addresses these assembly mistakes by giving each joint pair a unique finger pattern, which assures that incorrect pieces never fit. FoolProofJoint is a software tool that reduces risk of erroneous assembly of laser cut models by means of custom joints. The problem of erroneous assembly has been discussed in the field of manufacturing. If humans assemble manufactured parts, product designers need to design the parts so that they are easy to assemble. This is known as design for assembly, or DFA for short. Under the term DFA, many design principles have been proposed. I will introduce one example that is related to FoolProofJoint. Parts should be designed to prevent misassembly. For example, the square part should be assembled with the hole on the right side, but it can be misassembled in a flipped orientation. A notch on the part can prevent this kind of misassembly. However, DFA is done manually and is an expensive process. This only makes it applicable for manufacturing. FoolProofJoint automatically applies DFA to one-offs. In this project, we focus on laser cut models. Here are some examples that improve the assembly process of laser cut models. Roadkill points users to matching pieces directly from within the 2D layout, reducing visual search and speeding up assembly. And Daedalus in the Dark laser cuts haptic path in the plates to make assembly instructions accessible to blind users. FoolProofJoint introduces the concept of automated DFA and applies it to laser cut models to reduce assembly errors. Now, I'll talk about the two-step FoolProofJoint algorithm. In the first step, FoolProofJoint creates joints in a way that maximizes interchangeability and symmetry in the model. In the second step, FoolProofJoint prevents assembly errors by making joint patterns distinct when necessary. Let's start by looking at the first step in more detail. This step is an optimization problem, and let me show you why that is the case by using a simple example. Take a look at the cube model. It would be ideal to make all 6 pieces interchangeable and symmetric, but it is not possible to do this. The reason is in the corners of the cube. Only one piece can fill the room in each corner. In this corner, the top piece is filling the corner. A cube has 8 corners and it is impossible to equally distribute them across its 6 pieces. Therefore, there is no way to make 6 identical pieces. The best solution is to create 2 sets of pieces, which is the solution that you are seeing here. If we take a closer look at the corner again, you can see that its design can be described as the order of the 3 pieces that are involved. The top piece is extended all the way to the corner, the right piece has a finger that only touches the corner, and the left piece fills in the rest. This is an abstract description of a corner as an order of 3 pieces. Now let's see how FoolProofJoint finds this solution. FoolProofJoint starts by assigning primary corners. It tries to fill the corners with as few pieces as possible, which is the top and bottom piece filling all the primary corners. Then, it assigns 8 secondary corners to 4 side pieces, resulting in 2 corners on each piece. After the primary and secondary corners are filled, the remaining corners then become tertiary corners. After the order of pieces is defined for each corner, FoolProofJoint fills the remaining parts of the joints with alternating regular patterns of fingers and cutouts, finally creating these pieces. Now, let's look at this more elaborate example. FoolProofJoint starts by finding pieces that are interchangeable and rotationally symmetric. FoolProofJoint gives high priorities to the pieces which have a shape with high interchangeability and symmetry, and they will be handled first. Let's see how this plays out for the legs of the chair. The analysis of pieces resulted in these priorities. FoolProofJoint thus first assigns primary corners to the high priority piece. Then, it continues to assign secondary corners to the mid-priority pieces. In order to ensure the 2 pieces fills the same number of secondary corners, FoolProofJoint assigns 1 secondary and 1 tertiary corner on the shared edge to each piece. And again, foolproof joint fills the remaining parts of the joints with alternating regular patterns of fingers and cutouts. Foolproof joint uses this heuristic to design joints for the entire model. This is the result which is optimized for interchangeability and symmetry. However, a problem remains. These two joints are exactly the same and the pieces could be exchanged. This is a problem because these two pieces look similar, but they have slightly different sizes. The similarity of these pieces make it easy to confuse them by users. As a second step of the algorithm, foolproof joint solves this problem by making the confusing joints distinct. I'm going to show you how it works. First, foolproof joint finds pieces that have the same joint pattern as they can be potentially misassembled. In the chair model, the backrest and the side pieces have the same joint pattern with the front leg piece, so they can be wrongly assembled instead of the front leg piece. Next, foolproof joint only looks for the piece similar to the correct piece. To detect the similarity between pieces, foolproof joint uses a turning function proposed by Ni, Black, and Yin. Now, foolproof joint differentiates these two joints. In this example, foolproof joint changes the joint on the front leg. However, updating a single joint pattern can break interchangeability and symmetry. To preserve these properties, foolproof joint updates multiple joint patterns at once when needed. For example, this is the joint that foolproof joint updated earlier. Foolproof joint updates the joint and the mating joint accordingly, and it also updates other joint patterns to maintain interchangeability and symmetricity. This is the final chair model that foolproof joint produces after running both steps. We conducted a technical evaluation. We used 217 models from the Cube repository. For 97% of the models, foolproof joint produced a result that cannot be misassembled. The 3% of models that could still be misassembled contained edges that were too short to allow foolproof joint to create varied joint patterns necessary for distinction. For 65% of piece groups with the same shape, foolproof joint succeeded at making all the pieces in the respective groups interchangeable. Foolproof joint made 47% of pieces with a symmetric shape fully symmetric by providing them with matching joint patterns. Please note that it is not possible to achieve a score of 100% for the last two metrics, since making pieces interchangeable and symmetric is not always possible as demonstrated by the cube example. Foolproof joint automates and applies design for assembly guidelines to laser cut models by making pieces interchangeable, symmetric, and creating distinct joints. While design for assembly is a tedious and expensive process that has traditionally been reserved for manufacturing, with foolproof joint, we propose automating DFA, thus making viable to apply to personal fabrication. I would like to thank my wonderful co-authors. Thank you for listening.